All right, welcome to 322 Orbital Mechanics. This is going to be a longer presentation, but we can get through it together. So we're looking at orbital mechanics and be able to look at their shapes, their sizes, so therefore we can look at satellites and how they interact to lead into the future lessons for us. So an orbit, pretty much a closed path that the planet or a satellite travels. Kepler discovered the paths for the orbits were ellipses, not circles, in the 1600s. Satellites, they could be natural or human-made. They orbit the Earth in the shape of an ellipse. And elliptical orbits remain fixed in space, and Earth spins under a fixed satellite orbit itself. So they've got the racetrack analogy, where a car drives around a fixed racetrack, much like a satellite travels around the orbit. Natural satellites are like rocks or debris or like meteors and stuff that goes on there. So we're going to just go around and talk about a little bit of stuff there through them. So what is an ellipse? If you've studied it before in your geometry class, you got your conic section, you're cutting at that diagonal there. There's major axes and minor axis and semi-minor and semi-major there. So that angle being and slicing through, be able to look at. So just that's the ellipse, that shape that's going through. So what is an ellipse? So the circle we've studied before, that's everything equidistant from one point. The ellipse has two foci instead of just a center, and the sum of the distance of A and B is consistent, is like a constant for us that's there. So a circle would be like both foci are the same. So looking there where you could have like the Earth in the center, but then there's two different focus points to work through. So here's different types of, and dig into the equation. A defines half of the major axis, and B defines half of the minor axis. So the major axis is the longer one, minor is the smaller. So you have A from center to side, B from center to top, or you could switch and rotate it long ways, just major being larger there. And C is the distance from the center of the ellipse to the focal point. So from center to the focal point is your distance C, so 2C, the distance between those. For a circle, just back reference that, A and B are equal to the radius, and both focus points are located in the center, so that distance C is just 0. That's there. So we've got introduction to orbits, so the different orbits moving through. You can see the dots that are circling along there. Each one of them have different axes and different things to be able to look at. So what we're going to study here in the next couple slides is changing that orientation and how far and the length of it and everything else as it goes through. So just a different 3D model to show the different orbits as they circle around the Earth. So you got 4 of them that are different ones there. So basic orbits. That basic orbits is just looking at some different ones here. We'll study all of these different LEO, MEO, HEO, and GEO here in the next couple slides to describe them. But just going through, they have their own period to go and look at. And then each one of these different orbits has a different purpose for where they are going and what type of the Earth and everything else that they're covering. So if you want a satellite to, broadcast satellite radio to something, it's got to have its own orbit that's there. So there's sun synchronization as it's going here and popping up, where you can line it up with the sun, so therefore you're getting data, or you're always looking at a camera. It's always the sun underneath it to go through, to work through. That's there. The MEO, medium Earth orbit, that's here. So the medium Earth orbit works great. There's lots of different areas that it covers. So GPS satellites go on the GEO there, and they can track, so 3 dimensions, so 3 different points, be able to work through and analyze with those. So there's a coordination between all those to measure GPS. Let's see, what do they got next for us? HEO, high elliptical, so as it's going through. They spend a lot of time high above the North Pole, and they move very quickly to the south, so as it comes through, it'll go a little bit quicker. So there's a lot of times, because it's further north and more with transition to like Russia and those that are higher latitude and longitude as it's going through. So different countries have to send it out at different elliptical orbits, so therefore they could do different things with them. Geosynchronous. So it's rotating around the Earth. So they got the 3 geo that are going through and talking to each other. So therefore each one of those geosynchronous running around the equator there, going through and be able to look at different portions of the Earth at the same time. Here's all the different satellites in space. So orbits, how we describe them. Orbits are described by a set of parameters called orbital elements. 6 different parameters. 2 of these describe the size and shape, 3 orientation, and 1 describes the location within the orbit itself. So eccentricity. Eccentricity describes the roundness of it. So you can calculate the eccentricity. It goes from 0 to 1, so eccentricity is just the square root of 1 minus minor axis squared divided by the major axis squared that's there. Eccentricity value between 1 and 0, or 0 and 1 for closed orbits. So if it's just 0 means it's just circular for us. Eccentricity of 1 or greater means it's not closed, so it would just project out and never really come back for us. So if you're going to send something way off distance into space, we would use a greater than 1 that's there. So here is just a different video to show the different eccentricities of them. So the circle, red, is just there, eccentricity of 1. Then orange gets a little more oval shape as we go through, so that's 0.4. 6 for being the pink one that's there, so it's a little bit more. And then even more elliptical would be the green one that's there. So as we rotate and look around at the different orbits to go through, each one of them takes the same amount of time to go around, if you're noticing. We'll just look at that here in a second. But they all have different shapes to them that's there. So the next thing we look at, the size of the orbit itself. So the size of the orbit is half of the largest diameter, or the major axis that's there. So the semi-major axis is what we're looking at. So then semi-major axis origins from the center of the orbit. So since we are on the Earth itself, it's hard to look at there if the center is over there to work with. So just looking at some different lengths to try to go through. So different points of an orbit. Apogee, point of the orbit where it's furthest from the Earth, or perigee is the closest to the Earth. Apergy, altitude, is the distance between the surface of the Earth and the apogee, and then the same thing with pedigree, altitude, be from the Earth to that altitude there. So it's a distance between those two as it goes along. So if you have a circular orbit, everything is nice and orbital, so everything is equal. Of course, just like in your math language, perfect circle can't be achieved, so therefore you've got at least a little bit of elliptical shapes that are going through there. So how do you figure out the altitude of circular orbit? Kind of just taking some information and plug it in. So you've got the orbital period is equal to 2 pi times the semi-major axis raised to the 2/3 divided by the square root of the gravitational parameter, or you could just say 2 pi times the semi-major axis to the 3/2 divided by universal gravitation constant times the mass of the body that's there. So both of those equations work for us. Since we know the mass of the Earth and the gravitational constant, we would more or less use this second one for what we're calculating here on Earth itself. So as we mentioned before, we can go ahead and look at all of those points. We're starting out the same. going through the distance, so the circumferences are changing. The one in the white is earlier is going to go through and rotate quicker, so it has a greater period. As the A gets bigger, the period gets larger, so therefore it takes longer for it to go and circulate around the Earth there. So they're all starting in the same place. The larger the circle, the longer it takes to get around. Semi-major axis. These orbits all have the same major axis, but their eccentricities and their orientations around Earth are different. So you can look at the different periods that are going through. So all of them hit apogee at the same time. They're hitting the points at the same time, even though they're different angles and different stuff like that. They've all got the same time period of circling around the Earth that is there. So describing the orientation, orbits have identical sizes and shapes, yet they can differ in orientation and space. So there's inclination, there's right inclination, the ascending mode, and the argument of the pedigree. So there is one set there, and you're measuring how far off of that point that's there. So each one of these has a different inclination that's there. So inclination is based off of the equator. So how many degrees is it off the equator? So we've got the green line kind of going through the plane is the equator. So 5 degrees, 25 degrees, 45, and 75 degrees above the equator that's there. So the question, which one will orbit first? So all of them left from that one point. Everything stays the same, just the inclination. So everything is the same there for us. We can rotate this to look at it all laying on top of each other if we needed to. All we did is change the inclination off of that. So as you see, they're all covering different parts of the Earth depending on what we want that satellite to go ahead and do. So now you can go ahead and find into the Google Classroom page the orbit types assessment, and you can complete that, and then you should be good.